I want you to imagine a game of hot or cold. You're blindfolded. You have no idea where you are in the room. You have no idea where the target is. You take a step forward, your friend yells, warmer. You take another step, your friends yell, colder. You turn left and step, your friend screams, freezing. This childhood game is exactly, and I mean exactly, how a neural network learns. When we initialize a neural network, it is blind. It has random weights. It has no concept of what a cat looks like or what the next word in a sentence should be. It is just guessing randomly. The network takes a guess, it outputs a prediction, and then it waits for the voice. That voice yelling, warmer or freezing. That is the loss function. Without a loss function, ChatGPT is just a random character generator. Without a loss function, a self-driving car is just a hunk of metal driving off a cliff. The loss function is the mathematical scorecard of AI. It is the only thing connecting the model's hallucinations to reality. It quantifies exactly how wrong the model is, so the model can fix itself. Today, we are going to tear apart the three most important equations in all of deep learning. First, mean squared error, or MSE, the engine of regression. Second, binary cross entropy, the logic of yes or no decisions. And third, categorical cross entropy, the brain behind LLMs and next token prediction. By the end of this video, you won't just memorize these formulas. You will understand the specific mathematical mechanism that guide an LLM from speaking gibberish to writing poetry. Hello everyone, welcome back to Sumantra Codes. I'm Sumantra, and if you have been following our series, you know we have discussed the architecture, the neurons, the layers, the universal approximation theorem. That's the engine. But an engine needs a GPS. It needs to know where it's going. That is the loss function, also known as cost function or objective function. Now, before we write any math, I need to clear up a massive misconception that trips up almost every junior engineer. We do not train on accuracy, we train on loss. Why? Imagine you are taking a multiple choice test. The question is, what is the capital of France? Student A answer, Paris, correct. Student B answer, London, which is wrong. And student C answers the moon, which is absurd and wrong. If we judge by accuracy, student B and C are equal. They both got a 0. They are both just wrong. But you and I know that student B is much closer to the truth than student C. London is at least a city in Europe. The moon is a celestial body. A neural network needs to know that difference. If the gradient descent algorithm sees 0 for both, it doesn't know which way to move. It's stuck. But a loss function is continuous. It gives a score. Student A gets a loss of 0.0, student B gets a loss of 0.5, and student C gets a loss of 100. We need a smooth, differentiable landscape so we can use calculus to slide down the hill. We want to punish the moon exponentially more than London. This nuance allows the model to learn direction. We denote loss as j theta or L. Our entire goal in machine learning is remarkably simple. Find weights or theta that minimizes j. We are searching for the global minimum. Let's start with a simple problem of regression. This is when we want the AI to predict a continuous number, such as predicting house prices, e.g. $450K, predicting a temperature, for example, 72 degrees Fahrenheit, predicting the time until engine fails. Imagine you throw a dart at a wall. Label Y or target is the bullseye, the actual price of the house, which is, let's say, $500K. Y hat or prediction, where your dart actually landed, is the model's guess, which is, let's say, $450K. The distance between them is the error or residual. Error is y minus y hat. In this case, 500K minus 400K, which is equal to 50K USD. Now, if we have 1000 houses, we have 1000 errors. Some are positive, some are negative. If we just add them up, minus 50K and plus 50K would cancel out to 0, making the model think it's perfect when it's actually terrible. So, we need to make everything positive. We have two choices. We have first absolute value, which is absolute value of y minus y hat, which is also known as MAE. And the second one is square the difference, which is y minus y hat squared, which is MSE. Deep learning almost exclusively chooses option 2, mean squared error, or MSE. MSE is equal to 1 upon n sigma I from 1 to n bracket yi minus y hat I whole square. Why do we square it? Why is the square so special? This is a critical senior engineer question. There are two reasons, one practical, one theoretical. Reason 1, punishing outliers, or the strict teacher. Let's compare error versus squared error. For a small mistake, error is equal to 2 and squared error is 4. For a medium mistake, error is 5 and squared error is 25. For a large mistake, error is 10 and squared error is 100. Notice what happened. As the error grew linearly, the MSE function screams at the model, I can tolerate small errors, but I will not tolerate giant ones. It forces the model to prioritize fixing the worst predictions first. If one house prediction is off by $1 million, the loss explodes, and the model focuses all its attention on fixing that one house. Look at the V-shape or the absolute error. At the very bottom, at 0, the point is sharp. It's a corner. In calculus, you cannot take a derivative of a sharp corner. It's undefined. This means when the model gets really close to the answer, the gradient becomes unstable. It bounces around. Now look at the parabola. Squared error. It's smooth. It's curvy. The slope gently approaches 0 as you get to the bottom. This allows gradient descent to slide perfectly to the center, slowing down as it gets closer, like a golf ball rolling gently into the hole. However, be careful because MSE punishes outliers so hard if your dataset has bad data, like a house listed for $5 when it should be $5 million. MSE will destroy your model trying to fit that one typo. In those cases, we might switch to human loss, but that's a topic for another day. So now let's switch gears. What if we aren't predicting a number? What if we are predicting a category? Is this email spam or not spam? Is this tumor malignant or benign? Is this image a hot dog or not hot dog? This is binary classification. The output isn't a price like $500K. It's a probability between 0 and 1. We use sigmoid activation function to squash the output. Let's try to use MSE here and see why it fails. If the answer is spam, y equal to 1, we predict 0.9. The error is 1 minus 0.9 square, which is equal to 0.01, which is a small loss. But if we predict 0.1, dead wrong. The error is 1 minus 0.1 whole square, which is 0.81. The penalty is 0.81. Okay, it's not huge, it's less than 1. MSE is too gentle for classification. We want a penalty that goes infinity if the model is confidently wrong. We use binary cross entropy or BCE, also known as log loss. So the loss is equal to negative of the expression y dot log y hat plus 1 minus y multiplied by log of 1 minus y hat. I know that looks scary, but let's decode it. It's actually just a switch. Since y can only be 0 or 1, one half of the equation always disappears. Case 1. The truth is a spam or y is 1. The second term 1 minus y becomes 0. The equation simplifies to loss of negative of log y hat. Let's plug in some numbers. If prediction is 0.99, which is correct, negative of log 0.99 is about 0.01, which is a tiny loss. If prediction is 0.5, so let's say it's unsure, the negative of the log of 0.5 is about 0.69, which is a medium loss. If prediction is wrong, let's say 0.01, negative of log of 0.01 is about 4.6, which is a high loss. And if prediction is, let's say, very wrong, let's say 0.00001, the negative of log of 0.00001 is about 11.5. Wait, you might say 11.5 isn't that big compared to MSE's 100. But probabilities are small numbers. In a world of gradients, log loss provide an extremely steep slope when you are wrong. Crucially, if the prediction approaches 0, the model says impossible. The loss approaches infinity. This is the penalty of arrogance. If the model says there is a 0 chance this is a spam and it is a spam, cross entropy destroys it. It says you were confident and wrong. Infinite punishment. This forces the neural network to never be dead wrong. It encourages it to be humble until it has proved. There's another reason we don't use MSE for classification. If you plot the MSE loss surface for a classification problem with sigmoid, it looks like a wavy egg carton. It has bumps and valleys or local minima. The hiker gets stuck. If you plot cross entropy, it is a perfect smooth ball or convex. The hiker always slides to the bottom. Now let's go to the reason many of you clicked on this video. Large language model. How does ChatGPT know that after the word the next word is likely cat? or sky, but probably not multiplication. It uses categorical cross entropy. This is just binary cross entropy but expanded from 2 choices to n choices. When an LLM predicts the next token, it is solving multi-class classification problem. It isn't choosing yes or no, it's choosing one word out of vocabulary of 50,000. Let's say the sky is fill in the blanks, dot dot. The target y is blue. How do we represent blue mathematically? We can't use the number 452. That would imply blue is closer to the word 453. We use one hot encoding. It's a list of 50,000 zeros with a single one at the position for blue. The model outputs a raw score or logits for every word, and we pass it through the softmax function. Softmax turns scores into probabilities that sum to 1.0. So we have blue as 0.8 probability, gray as 0.1, red as 0.05, and pizza has 0.00001. The loss function compares the probability distribution of the guess to the probability distribution of the truth. So the loss function is loss is equal to negative of sigma I varies to 1 to n yi minus log y hat I. Look closely. Since the actual vector y is all 0 except for the correct word blue, every term in the sum becomes 0 except the one for blue. The math simplifies beautifully to loss is equal to negative of log of probability of correct word. We literally ignore everything else. Did the model predict pizza with 10% probability? We don't care directly. We only care what probability did you give the correct answer. If you gave blue 0.9, loss is small. If you gave blue 0.3, loss is high. The model works tirelessly to push the probability of the correct token as close to 1.0 as possible. By doing so, it naturally pushes the probabilities of pizza and multiplication down to 0. You will often hear LLM researchers talk about perplexity. My Llama 3 model has a perplexity of 4.5. What does that mean? Perplexity is equal to e to the power of loss. Perplexity effectively measures how confused is the model. A perplexity of 1 means the model is perfectly certain. It knows exactly what word comes next. A perplexity of 50,000 means the model is just rolling a die with 50,000 sides. It knows nothing. Your goal in training an LLM is to drive perplexity down. So we have these formulas: MSE, binary cross entropy, categorical cross entropy. What do we do with them? Imagine a vast multidimensional landscape. The x and y axis are the weights of your neural networks, all 175 billions of them. The z-axis height is the loss. When we initialize a neural network randomly, we are standing on top of a mountain. The loss is high. The model is dumb. If you want to get to the bottom of the deepest valley, that point is called the global minimum. That is where the loss is lowest, and the model is the smartest. The loss function defines the shape of this terrain. If you pick the wrong loss function like MSE for classification, you create a landscape full of jacktrap, flat plateaus, and fake valleys or local minima. The hiker gets stuck. If you pick the right loss function like cross entropy, you create a smooth, steep slope that leads directly to the bottom. In our next video, we'll discuss gradient descent, which is the method the hiker uses to determine which way is down. But remember, loss function is the hill. If the hill is shaped wrong, no amount of walking will save you. So let's recap the scorecard of AI. Optimization is not equal to evaluation. We optimize loss, not accuracy, because loss provides a smooth differentiable gradient that tells us how wrong we are. MSE, the strict teacher, use this for regression on numbers. It squares errors to aggressively punish outliers and create a nice parabolic curve for the gradient. Binary cross entropy, or the penalty for arrogance, use this for yes or no classification. It punishes confident wrong answers with massive loss, forcing the model to be humble. And finally, categorical cross entropy, or the LLM engine. Use this for next token prediction. It focuses entirely on maximizing the probability of the correct word. Understanding loss function changes how you debug. If your loss is stuck, ask yourself, am I using MSE on a probability problem? If your loss explodes to infinity or NaN, ask yourself, did my model predict 0 probability for a true event? I want to hear from you in the comments. What is the weirdest loss value you have ever seen in training? Did it go to negative? Yes, some loss function can. Did it hit NaN? Let me know your horror stories. If you want to see how we use this function to actually update weights, make sure you hit that subscribe button and ring the bell. This has been Sumantra Codes. Keep minimizing that loss. I'll see you in the next epoch.